yeah, thank you for the organizers for inviting me. They might regret asking me to give this talk, but you know, well, I'm from Canada, and I would also like to share the views on optimal transport of a very famous Canadian philosopher. So as the difficulty of optimal transport, like Drake in his famous album, like in 2016, he said, OT, OT, there's never much love when we go OT. So hopefully, I pray that I get back in one piece after this workshop. But anyways, the workshop has been a lot of fun, and I've seen a lot of love from the OT community, so thanks, guys. But all right, let's get back to actual optimal transport. So, okay, I guess you're tired of hearing this, right? So we have the classical entropic optimal transport problem. I have a cost matrix C with real entries, and I have the target marginals that I want to achieve. And the output here of the entropic version of formulation of the matrix of entropic optimal transport is, okay, I want to find like a transport plan that minimizes the KL divergence between P and like this matrix A, where A is the exponential of minus cost, right? So that's the classical one. And we also know that the optimal solution to this problem has this form, like has this scaling form, right? That I have like a diagonal matrix here. So this is, you should think of a diagonal matrix with the vectors like x1 up to xn times A times diagonal of y. And it's just the scaling of the matrix A of your exponential of the minus cost matrix, right? That has the right marginals, right? Okay. So, and this is kind of known as a scaling problem from other communities. And, you know, today I'm going to ask the question like, and by the way, it's 9 a.m., so this talk is going to be like, the math is going to be very easy, very simple. Okay, the motivation is, it's nice. We're going to see a very nice proof of Sinkhorn. But here's the question, right? So what happens when our cost now is allowed to also be infinite, right? Because you know that, okay, I have this scaling problem. All of you are tired of hearing as well about Sinkhorn, that you can always scale Sinkhorn, and then Sinkhorn always will converge it to the right answer, right? But Sinkhorn's theorem, right, requires all the costs, like every entry of your matrix to be positive. Now, what happens when we allow like infinite costs? And this has real world applications, right? Because just yesterday you realized, right, like in some factories, like if you think of the Kantorovich like relaxation, if some factories now impose tariffs on everybody else, and then the cost of all the goods become infinite. So sometimes people stop buying things, right? So you can't transport mass from one place to the other, right? So here, equivalently, our matrix now, instead of being like just having just positive entries, it will have non-negative entries. Now the question is, like, does this problem have a solution at all, right? Okay, so, well, we're going to use the same algorithm, so I'm just going to recall like the Sinkhorn or RAS algorithm, right? So again, I have an input now, and my matrix will have non-negative entries, and I still have my target marginals, and I have this approximation parameter epsilon. And what Sinkhorn does is, I just want to get an epsilon approximation, a matrix that will satisfy these marginals up to precision epsilon. Okay, so just to give some notation, like for any matrix B, I'm just going to say like RB is the vector that gives me like the row sums like of the matrix B. So it's giving me one of the marginals. And then here I'm getting the other marginals, right? Like the column sums. And here this delta function is just saying what is the distance of my matrix from satisfying like the two marginals, okay? So, okay, so what does Sinkhorn do? For t iterations, I'm going to alternate between normalizing the rows, right? So this is going to be my row normalization. So here, the first step, I make the rows all sum to 1, and then I normalize to make this row sums to r. And then the second step, I'm going to normalize the columns. So here, I first make all the columns 1, and then I normalize to the target columns, and then I keep going. And if at any point my distance becomes less than or equal to epsilon, I return, right? So that's the usual algorithm. Great. Okay, and what does Sinkhorn prove? He says when A, sorry, this should be an A, has only positive entries, right, and my marginals are like uniform, then the above algorithm always converges. Okay? So, but then I'm a computer scientist, so I always ask, okay, so how fast? Like, what is the number of iterations t that I should choose, right? And another question is, oh, this should be an A again. What if A has only non-negative entries? Will this like always converge, right? So, okay, let's look at one example, right? So there's two examples here with non-negative entries. So let's look at this first example. Well, clearly, if I have my uniform marginals, like clearly this matrix will never be close to having uniform marginals, right? Because if the marginal of this guy, if this first row has to sum to 1/3, right? But this guy has to sum to 1/3, like this column has to sum to 1/3, this column has to sum to 1/3. So you'll never be able to scale this guy to doubly stochastic. So clearly the problem is non-trivial there. So sinkhorn, like there must be a criterion for sinkhorn to work or not work, right? But if you run sinkhorn's algorithm on this one, it will converge, okay? And okay, what is the difference between these two examples, right? So, okay, so the reason why this first matrix does not converge is because it has this big block of zeros here. And how big? Well, it's the dimensions of this block of zeros, like if I sum the row and column dimensions of this block of zeros, is bigger than the dimension of the matrix, right? So this dimension is like 2 + 2 is 4, it's just bigger than 3, right? So this is what I will call like a big block of zeros. It's also called the Hall blocker, right? And on this side here, there's not, well, of course, there's no like 2 by 2 block of zeros or 1 by 3 block of zeros, right? You can just see it, yeah?
But isn't it also because just we have like two like repeating vectors, you know? Like,
no, you can
or
put,
like two columns are identical, so this matrix is not.
no, yeah, not really, because I just put ones just because I don't know two big numbers, right? But you can put like 10 and pi here, and it doesn't matter, right? Because once you scale again, it's going to be 1/3, 1/3. So yeah, it's not about those numbers that appear. It's just about the support, actually, right? But you can ask many questions. Is this, and I guess you're probably reading my other slide, right? Is this the only obstruction, right? Or if I change the entries, can I also not have scalings, right? That's also a good question, right? Right now, I just gave you one. Okay, one obstruction is this big block of zeros. And if I have this, it's clear. You'll never be able to get close to doubly stochastic. But if I don't, will I always be able to get close to doubly stochastic? Or is there something else? Yeah? Okay, so, and okay, can sinkhorn, like this RAS algorithm, identify like which case, right? And is this the only obstruction? So those are two questions that we're interested in answering. And okay, well, so what Hall's theorem tells us about the support, right, the Hall's marriage theorem, is that only one of these above cases can happen, okay? So, and what is the other case? What do I mean that, well, because right now you said, well, there's a big block of zeros and no block of zeros. But here, you can see that in the second matrix, we actually have a matching if I look at the support of this matrix, right? So if I look at my matrix here as saying like 3 points, 1, 2, 3, 1, 2, 3, I can draw a graph. And I'll say, if there is an edge, if there is a 1 in the ij entry, I'm going to draw an edge between these two guys. So for example, this is my entry 1, 1. I have a 1 over there. My entry 1, 2, 1, 3. And then 2 will have an edge between 2 and 1 and 2 and 2. And the third one only has an edge with the first one, right? So here, what can we do? Well, in this bipartite graph, I have a perfect matching, right? I can pair 3 with 1. I can pair 2 with 2. And I can pair, I don't know, 1 with 3, right? So I have a perfect matching here. And Hall's theorem says, OK, either my matrix will have a perfect matching, which corresponds to a permutation. So what is the permutation that comes from that matching? Is this, 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 right? So either I have a permutation with support, with positive entries, or I must have a big block of zeros, right? It's a very simple theorem from combinatorics, right? And this actually turns out to be like a very special case of the Hilbert-Mumford theorem in invariant theory. And invariant theory is always like at the background of what I'm thinking here. So if you want to talk to me about it more, we can talk about it later, but I don't want to overload everyone at 9 a.m., right? So we'll stick to Hall's theorem. Sounds good? So only those two cases can happen. Either I have a permutation, like support on a permutation, or I have a big block of zeros, okay? All right, so, and before we talk about like the analysis of sinkhorn, I want to say, by the way, the scaling problem has applications even beyond the ones that everyone mentioned, and I just wanted to say some of them, right? So for example, matrix scaling was used in the 90s to give a deterministic approximation of permanence of non-negative matrices, okay? It's a terrible approximation, but it's pretty good compared to whatever else you can get. Also, numerical analysis is used in preconditional matrices. It's also used in extremal combinatorics for generalizations of Sylvester-Galai theorems. And there's many more. If you see like the survey by Idel, and also, well, Pere Couture, you guys know. So, okay. So let's talk about our problem then, and let's talk about analyzing this algorithm, right? So, okay. So here, my scaling action will be what? I take x and y, and the action that x and y is having on A is just multiplying on the left, like x scales A on the left by the diagonal of e to the x, and y is scaling the columns of A, right? And again, just for this talk, but we can talk about general marginals. Everything we do here works for general marginals, but things get a little bit more technical, so we can talk about it offline. But let's always consider just uniform marginals. And here, we can assume that these matrices here, these diagonal matrices, they have determinant 1, because otherwise, like if you notice, if I divide here by like a multiple of the identity, what am I doing to my marginals? I'm just kind of scaling them up and down, right? So I can reach the marginals like 1 over n if by scaling with matrices with determinant 1, I can get a multiple of the all ones vector, right? And then I can just use the identity to normalize everything. Sounds good? So, okay. So, all right. So now here's a function that I would like to study, okay? And this function is motivated by invariant theory, okay? So if you know this, like this function is also called like the Kempf-Ness function, okay? For those of you who know a little bit about invariant theory. That's why like I'm not pulling this function out of nowhere, okay? Like we're studying orbits here. So, okay, so what is my function? I'm going to take, this function is going to go from like Rn by Rn, which is my x and y, and I have values in R, which is going to be the log of the norm of the action of A, right? So I have my matrix A, and what are we doing to it? We're scaling on the left and on the right. So let's say in this case I have x1 up to, well, e to the x1, e to the xn, and then I have e to the y1, e to the yn, right? And if you think about this, like in this action, I have A here, and if I draw all the points that, all the matrices that are reachable by this, I get an orbit, right? So, and I'm like, any point on this orbit has this form, right? And in invariant theory, they are interested in figuring out like, okay, can I have like a canonical representative for this orbit, right? That's a very important problem in invariant theory. And what they're saying, like, okay, what would be a good candidate? Well, let's take the point of minimal norm in this orbit, right? And that's why they're studying like this log norm function, okay?
Which norm is it?
Ah, exactly. Which norm is it, right? Because we're doing matrix scaling, this norm will just be like the one norm of the matrix when I consider it as a vector. So it's just the sum of all the entries, of the absolute values of all the entries, yeah? But since here everything is positive, right? Like my matrix is non-negative, and these vectors, like these exponentials are always like positive numbers, I'm just taking the sum of all the entries, okay? So we can just study this. Very good. Right. You can study these, and like people study this. I mean, in invariant theory, they usually use the norm that comes from the group action on the vector space. So the vector space has a norm, and they use that one. But if you want to use different norms, and we actually do use it for different applications, it also like you can also use and optimize, right? So long as you can optimize, you're in business. So, but it depends on your downstream application.
But I guess here the one is useful because if you are uniform after scaling, then the log kills it, right? Or not?
No. So, not yet. Let's just, yeah. It's really, yeah, the one is useful is just because it's the usual thing that you do when you're doing the sinkhorn, right? Yeah. Okay? So, and now, if you do the calculation, and it's just kind of undergrad calculus, you're going to figure out, okay, this function turns out to be convex. Okay? So, in this Euclidean space. But the Euclidean here is really lying to you. So, and we're going to get to this point later. Because if you look at it, your action is this in this exponential, like in this image of the exponential, right? So you have a really a Riemannian thing going on. But because your group is commutative, things simplify. But let's keep with the convexity. So here, this is a convex function, okay? And if you believe me, then, okay, then we can minimize this, right? And so this is what we call like the log of the capacity of the matrix A, which is just the minimum of this log norm along this orbit, right? But the orbit may not be closed, so I need to put an infimum. So, okay, so really I'm minimizing over this orbit closure, okay? And now, here's the thing. Okay, so if I have a convex function and I want to minimize it, what am I going to do? I'm going to do gradient descent, right? So, okay, so let's talk about the gradient. And then once you compute the gradient, you're like, oh my God, right? That's crazy. What a coincidence, right? So, okay, before we do that, so notice that our function is equivariant. And what do I mean by equivariant? It means that if I take this f of a and I evaluate it at alpha beta, is the same thing as evaluating like f at 0, 0, but at a different scaling, which is the matrix B. It's just the scaling of A, right? So because of this equivariance, I only need to compute gradients at the identity, which is much nicer, right? So, okay, and identity here will be 0, 0 because I'm taking the exponential map. So, okay, so what's the gradient of this matrix? So if you do the gradient, I mean, and here, really, right, you could just take the differential by the xi variable and then, you know, like, so calculus one-on-one here, right? So the gradient of this matrix, of this function at 0 is going to be exactly how far your matrix is from being doubly stochastic.
Sorry, that norm is still the norm.
This is the one norm, like the sum of all the entries of the matrix. Yeah, yeah, exactly. Okay? And the fun fact, right, is that sinkhorn, I mean, and this norm we can kind of, like, this norm, you can just actually ignore it because once sinkhorn does the first step of scaling, like just to address a little bit also what Natalia's saying, the norm of your matrix is always 1 because sinkhorn is always scaling to have the right marginals. And if my marginal is uniform, right, the sum of all my entries has to be 1, right? So you can think of this norm as always like being 1. It always stays fixed. So sinkhorn is always like, so now if I would do the gradient descent, when my gradient is 0, well, that's when I have a minimizer because I have a convex function. So my point of minimal norm will be a doubly stochastic matrix, right? If this point exists, right? So, okay. And again, but how can this point not exist? Well, the point will not exist if this function does not have a minimizer. But when does it not have a minimizer? It's when the log is minus infinity, which means that in the orbit, like 0 is going to be in the closure, right? So really, when you're talking about the scaling problem, when you talk about this norm minimization problem, you're capturing like, oh, if 0 is in my orbit closure, that's when I'm never scalable to doubly stochastic. But when 0 is not in my orbit closure, then I will be scalable to doubly stochastic, right? That's what we want to prove, right? Okay, so great. And now, okay, so now you can actually see what sinkhorn is doing, right? So sinkhorn is a very kind of principled approach because sinkhorn is just doing block coordinate gradient descent, right? Because what does sinkhorn do? Sinkhorn says, okay, I'm going to look at this gradient. I'm going to ignore this one. And when I normalize, I'm just making this part of the gradient, this block of the gradient, 0. And then I go somewhere, right? That's easy to achieve. So you minimize along this direction. Now that you minimize this direction, it's like, well, but when I look at my gradient, if it's not 0, I'm going to make the second block 0. And I just keep alternating, right? But now you have a lot of different algorithms for sinkhorn. You can say, well, I don't need to do this block coordinate. I can just do gradient descent right away. Might be better, right? So, okay. And, Okay, so let's talk a little bit about properties of the log norm, just so we can actually fully prove this generalization of Sinkhorn for all cases, right? So, okay, so I know that if I take FA and I evaluate it at 0, 0, I just get the log of the norm, right? The sum of the entries, because this matrix becomes identity, this becomes identity, everything else becomes identity, so I just have the norm of A, right? And now, if B is either like a row scaling of A, or if B is a column scaling of A, doesn't matter, but the norm of B is equal to the norm of A, like the sum of all the entries is the same, which is what Sinkhorn does, right? So then the difference between the value of the function fb at 0 minus fa at 0 is exactly minus 1 over n times the log that of diagonal, right? And why is that? Because here, like, well, what happens here? I have fb 0, 0 is just going to be the log of the norm of B, right? And, well, and then, but what is this? So this is exactly equal to log. Now B is what? Is the diagonal Z times A, right? So this is going to be like diagonal Z times A. And then here, I'm just going to subtract this minus log of the norm of A, right? So when you do the calculation here, all you're going to get is you're going to get that, oh, I forgot to divide, sorry. I need to divide here by the diagonal, by the determinant. Oops. No, yeah, I have a typo there, sorry. I need to divide by the determinant of the diagonal of Z. Sorry, that's a typo there. Because again, I'm only going to do scalings with determinant 1, right? So I didn't enforce the constraint that the determinant's 1. And now once I have this is exactly the log, well, this is the log of the norm of B minus 1 over n log determinant of the diagonal of Z, right? Just because I normalized. Sorry, there's a typo here. I need to just divide by the determinant because remember, my scalings are all matrices of determinant 1. So I need to divide by the determinant, right? So here I have my scaling here. And then this norm of B, right, is the same as the norm of A. So then these guys cancel. And then I'm only left with the determinant, right? Okay. So now, oops. Okay, so these are the only properties I need. Now we're ready to analyze Sinkhorn, okay? All right, so again, just to recap, right? So for t iterations, I'm only normalizing like rows or columns, and now I'm just doing my uniform marginals, right? So I only care for now about the uniform marginals. For these t iterations now, what am I going to do? First, I'm fixing the row sums to be like, the rows to be 1 over n, the row sums, and here I'm fixing the column sums to be 1 over n. Okay, so, all right. Now, remember, either there's a big block of zeros, like this whole blocker, and then we know we never get close to double stochastic. But if I don't have a block of zeros, I know I have a permutation. I have a support in a permutation. So then let's use this permutation where I'm fully supported, okay? And this is going to be my invariant, okay? So what is my invariant? I'm just going to take like psi of A here to be equal to the product of these entries, like product of AI pi I. And why do I call this invariant? Is because if you think about it, oops. If I have an action on, let's say, x1, xn, a, y1, yn. And remember, these matrices have to have determinant 1, right? So the determinant of these matrices is 1. What happens to that function, to that polynomial function, right? Let's say that this is b. I have product of bi pi I is equal to product of, well, B is in the ith row, so I get multiplied by xi, ai by I, and y pi of y, right? But now if I pull out all of the, and this is I going from 1 up to n, but this is a permutation, which means that in the end I get product of xi, product of yi, product of ai by I. But these are 1. So this doesn't change anything. So this is an invariant function, right? So, does that make sense? So I have this invariant. So this quantity here is never going to change when I apply sinkhorn, right? So we're going to use that as our potential function, this invariant function. So this doesn't change, right? Okay.
And it is not negative, right?
And it's positive, yeah, because like all of this, right? All of these entries are positive, exactly, right? So, and now in particular, what happens? I know that because sinkhorn, right, is never changing, like no matter my scaling, remember this AT here is the matrix that I get at the tth step of sinkhorn, right? So we know that, well, what do I know? I know that this guy, so this is an invariant, right? So if I look at my matrix AT, I know that if I look at product of AT I pi I, this is the same as like my psi of A without the t, right? Because this didn't change as I apply sinkhorn. But each of these entries is less than the whole norm. So I can just say product I goes to 1 up to n of the entire norm of the matrix, because the norm is the sum of all the entries, and all the entries are non-negative, right? So I know that this guy here to the power n, my norm to the power n, is always bigger than this, which means that if I look at my function at the value at, this function is always, well, is equal to the log of my norm, but it's always bigger than this, right? So I know I cannot go to minus infinity, right? Okay, so this log norm function is always lower bounded by something finite. And now, oops, I see, I pressed the wrong button, right? I've seen you guys doing that before me. Okay, so this one, okay. All right, so now what happens here? Well, what happens if every time that we're doing the scaling, every time that sinkhorn is doing the scaling, remember, this delta here is just the distance of the gradient, or the norm of the gradient. If the norm of my gradient is always greater or equal to epsilon, which means I'm always far from being doubly stochastic, right? If I keep scaling and I'm always far from being doubly stochastic, what happens? Well, then, remember, what is the difference between the values of the functions, right, after one iteration of sinkhorn? Is exactly like 1 over n times the log that of my scaling, right? But now here's the thing. I'm just going to use a quantitative version of the arithmetic geometric mean inequality, okay? So just some very basic quantitative difference. And I'm just going to tell you, okay, look, if this vector here is far, because remember, right? If this guy was, remember, now I'm scaling the rows to be like by n. So if this guy was the all ones vector, right? Then, well, this guy would just be 1. Right? But that's exactly the maximizing of the geometric mean, right? So, but now if this guy is far from the all ones vector, then this product here, this determinant of diagonal, should also be far from 1, should be a little bit far from 1. And that's what I'm going to use. I'm going to use this quantitative version of AMGM and say, okay, if I'm far from being doubly stochastic, then what happens is that this determinant is also like upper bounded by this, which is strictly less than 1. Right? Does that make sense? So if I'm epsilon far, I'm this far. But now what happens? Well, okay, so if my gradient is always too large, it means that sinkhorn is making a lot of progress. Like my function at the time t plus 1 is less than the function at time t minus this epsilon n over 6. And now we're done, right? Because I started with a function like fa0, like at time 0, this is some number, is bounded. And I know if my gradient is always bigger than 0, it's going to decrease by epsilon n over 6. So, but I know that my function can never be smaller than this quantity, which is also a fixed amount. It only depends on the input. So therefore, I must converge. Does that make sense? And this holds for any epsilon. And this is the proof, right? So if you have a permutation, if you're supported in a permutation, then you're always scalable to double stochastic, and this is the proof, right? Does that make sense? So very elementary. We don't need like Hilbert metric or anything, right? So it's very nice and easy. Yeah.
Question, like once you already showed essentially that under your situation, you don't go to zero with your orbit. Essentially, that's what you showed there, right?
Yeah.
Do you already have also some sort of strict convexity here or not?
No. So strict convexity would be, right, whenever you have like, I mean, when you look at the second order gradient, I mean, it has to be strictly positive, right? So that doesn't always necessarily happen when the matrix has non-negative entries. But it does happen when the matrix has full support. Yeah. And that's where you get the contractivity of the Hilbert metric. So that's
right. But also in this case, if you knew you were strictly convex and then you also bounded from below, you're coercive, I guess, then the gradient method should converge the minimizer.
Exactly.
Here you're not strictly convex.
Mm-hmm.
A priori.
Yeah, a priori, exactly.
Thank you.
Yeah.
Good question. So here, how do you use the assumption that like your A has like good support?
Right. This is when I constructed my invariant, right? So if there is a permutation where I have full support, right, and then I don't care what the entries are, I just care that they are bigger than zero. Yeah.
So not having full support is the same as just saying that all these functions are zero.
Exactly, right? And for those who know like the Hilbert-Mumford theorem, it just says it is exactly the same as saying like, so those orbits that we were talking about, these orbits that have zero in their closure, right? So those points, the set of all points whose orbits have zero in the closure, they're called the null cone, right? And the Hilbert-Mumford theorem says like, okay, if all my invariant functions, polynomial invariants, vanish on your point, then this point is in the null cone, which is in the set. Like, so if you take this orbit, it contains zero, okay? For those of you who know a little bit of that. And this works in really like large generality, okay? Which we will need for the second part of the talk. Oh, okay.
Rafael,
Yeah.
I just have to ask, has anyone looked at this from a gradient flow perspective?
From a great, yes. Because now that you know that, I mean, you don't need to use sinkhorn now, right? So I can just do gradient flow. And that's exactly like, so like Linden S did this, right? Like Kirwan also did that. So that was their famous works was exactly like looking at the gradient flow. So these convexity theorems and stuff like that, like, yeah, for sure. These are classical works in invariant theory.
And the advantage over sinkhorn is that the sinkhorn only applies when you can guarantee positivity of all the entries or something. I mean, you don't have, I mean, you need a little bit more to ensure convergence.
Yeah, exactly. I mean,
Yes.
it's more refined.
This captures the case where you have
Full support.
yeah, that's right.
Exactly, because then you can take any of those invariants, right? So because you have one.
Right. So, yeah.
Okay.
So one second. So how many steps do you need to go, to decrease to epsilon? How many steps?
Very good. So definitely I can get it from here, right? Because it will just be like f of a 0, like my original one, minus this quantity, right? Over like n over, well, epsilon. Yeah, you run
Linear in n.
linear in n, exactly. It's a linear number of steps, exactly.
That's that's because the sinkhorn algorithm, if you do it correctly, you have log of n, not m.
The n is the dimension.
This is what in Couture and other, that the number of iterations you need is the log of n.
Yeah, for sure. But I mean, but this is just a 9 a.m. analysis. I mean, I can do a little bit better, and I can show you that we can also do it. Yeah, it's not hard. Whatever they do there is not hard. Let me just say it like that. But it's 9 a.m. I don't want to. It's not, but it has work. Okay. So yeah. So okay, now let's be non-commutative a little bit, right? At last, I mean. So now. Okay, so we have the matrix scaling, and then now let me talk about from completely non-optimal transport. Like, you just look at matrix scaling, you're amazed by it, and it does a lot of cool stuff. And then you go, right, if you're Leonid Gurvitz, so Gurvitz in 2004 came in this and that. This is amazing. Okay, let's generalize this. So then he's like, let's generalize this to the quantum setting. So I have my cross operators, which gives me like this completely positive operator, right? And it's dual. And okay, now how am I going to scale a channel? So the scaling of a channel here will just be, I'm going to take, well, remember, the scaling in the matrix scaling, I needed this like positive scalings for the rows, right? So what's my generalization to positive? I'm just going to have like positive definite matrices here, P and Q, okay? And how am I going to act on my Krauss operators? I'm just going to multiply all of them at the same time by P and Q, right? Which is what in the first tutorial Dima was saying is this bimodule structure, right? So that's going to be my action, okay? So this is going to be the scaling of a channel. And now, what is my notion of doubly stochastic? My notion of doubly stochastic is just going to be that, okay, so an operator B is doubly stochastic if phi B of identity is equal to phi star B of identity, which is 1 over n, right? So, okay, so now, so these are so my question now, my matrix scaling question will be, okay, are there scalings P and Q, right, in positive definite scalings, such that this scaled operator is going to be doubly stochastic? So that's going to be my operator scaling question, right? It's just a generalization of the matrix scaling, okay? Sounds good? Okay, so, and again, we can also scale to arbitrary marginals, but we can talk about that later, okay? So, okay, so what are applications of these things? So first of all, there's applications in function analysis. For example, we're able to compute like Braskamp-Leib constants, for those of you who know. Well, there's applications in the Schrödinger bridge problem that Trifon was talking about, like solutions, algorithmic solutions to the Schur-Horn problem, like Paulsen problem. It also has connections to non-commutative algebra. If you want to know more, there's a survey that we wrote back in 2018, but there's going to be a book coming out soon which has a lot more of that information. Okay, but here's the thing. So Gurvitz in 2004 made this generalization, and he was like, you know what? I can also generalize the Sinkhorn algorithm, right? How do I do it? Well, okay, I just look at my distance to doubly stochastic, and now for t iterations, what do? I'm just going to alternate between, I'm going to make the first guy to be equal to the identity. So this is my normalization, so I multiply on the left. And if I multiply on the right, if I scale only on the right, I'm able to fix the dual. Okay? So I'm just going to keep doing that. So that's going to be my generalization of Sinkhorn. Exactly the same. And then if at any point my distance to doubly stochastic becomes less than epsilon, I return. Okay? So, okay. So, all right, so now let's kind of put that perspective of minimizing a norm, right, that we had from matrix scaling. So what's the norm of my operator here? My norm of the operator would just be like the sum of the trace AI star. Okay, that's my norm squared. And, okay, and my function of interest now, again, is the log norm, is the same function. But now, and again, this function now, it's acting on this Riemannian manifold, right? And it's going to be geodesically convex. But what's my function? I'm just going to take the log of the norm of my action here. And then I'm just going to have to subtract these determinants because, again, it's the same thing. If I can scale to doubly stochastic, I can scale with things with determinant 1, and then I can fix the proper scaling.
What's the norm?
Huh?
What's the norm?
Yeah, so this norm is exactly this one.
Okay.
That's why this one's more complicated, so I wrote. Yeah, it's just the Frobenius norm of every like AI. Yeah, or if you think of this as a big vector, right? This is the norm, L2 norm of the vector. Yeah, sounds good. Okay, so this function is pretty much like it looks the same as the matrix scaling. So now we did all that work on matrix scaling, so everything will work out the same. And again, the problem of interest that Gurvitz was studying, he wanted to minimize like this log of the capacity, right? And how do we do that? Well, okay, let's look at the gradient of this function, right? So, well, now I need to take the Riemannian gradient. And again, because this function is equivariant, I only need to compute the gradient at the identity always, right? It's the same thing that we did for the matrix scaling. Okay, but how do you compute this gradient, right? So, well, remember, what's the property of the gradient? If I take the directional derivative with directions r and s, where RNS are Hermitian, right? Then this should be like exactly my derivative of my function when I evaluate t equals to 0, right? And if you do this calculation, right, you get exactly that's going to be, again, my gradient is this part here, which is my distance to doubly stochastic, right, of my operator. Does that make sense? So again, my gradient is exactly the distance to being doubly stochastic. Okay? And, okay, so it looks like we're getting very lucky, right? So what's the analysis, right? I don't have a lot of time, but essentially the analysis is like pretty much the same as matrix scaling. Oh, 10. Oh, then let's do it. But what's the difference now? Well, what is the invariant? The only thing that we need to figure out is, okay, what's the invariant that we use? Because clearly there are some operators that cannot be scaled to doubly stochastic, right? Just because this is, for example, this is a generalization of matrix scaling. So if you take the instances that correspond to matrix scaling, you know that you cannot decide. But now what are the invariants? So, well, but as it turns out, okay, there was much earlier work on this exact action, which is called like simultaneous left-right action. And we know that the invariants are going to be the following. So if my matrix, let's call my matrix of my cross operators, they're going to be like x1, xm, right? But now these are variables. I can plug in whatever cross operator here, right? Like, so what are my invariants? So it turns out that my invariants in this case, they're going to be these polynomials. Determinant of sum of xi tensor yi for any y. Okay, so these polynomials here, they're polynomials like...
And this y is unconstrained in size.
And this y is unconstrained in size, exactly. So they're all the same dimension, right? But for every dimension, you're going to have an invariant, exactly, right? And you can see that they're invariant because, look, if I act on this, on the left and right, by like matrices with determinant 1, well, what happens here? I'm just multiplying this guy on the left and right by determinant 1, which means I can pull out everything by the multiplicativity of the determinant, right? So these are invariants. And now what we need to know is, like, are these all the invariants? And the answer is yes. These are all the invariants. Okay? So, okay. And once you know this, now you'd say, okay, yeah?
So in the matrix scaling case, the invariant that you considered, those were the only possible invariants for this.
Very good. So, right. So, okay. And that's a great question because it's a caveat that I didn't explain that I'll explain now. So, what do I mean by these are all the invariants, right? This is a generating set of all the invariants, right? Because if I take, for example, in the matrix scaling case, I take two different permutations and I sum them, they also form an invariant, right? Because each of these, the products were invariant. So all we need is we need to generate the ring of invariants, right? The invariants form a ring and I just need generators for the ring, okay?
Why do you need to be sure that these are all?
Right, I need...
It suffice to have one to make the proof.
Exactly, because I need to know that they're all big, exactly because my statement is what? If I'm not in the null cone, right? If 0 is not in my orbit closure, then there is an invariant that is not 0. But if there is an invariant, I need to have the generators to figure out, to test which one is not going to be 0, right? Because there could be a really bad point that zeroes out like all but one of your generators. That's why I need all of them. Yeah? And in this case, like, these give me a basis of generators. Okay? And now that I have this invariant, I can play the same game. Right? Because I can say, suppose that my operator, my cross operator, is not in the null cone of whatever this action is. Right? So 0 is not in its orbit closure. I know that there is one of these guys that will not vanish. So what am I going to do? I'm going to use this guy as my potential. So that's going to be my potential. So I know, because, and again, I'm going to relate the value of this polynomial and my invariant to the norm. Right? So I do the same thing. So because this polynomial is going to be different from 0, the norm of my polynomial is going to be bigger than this like to some power, just like we did before, right? So I know that I can use this invariant, and now I can scale again. And then the proof is verbatim. You just apply everything that we did for the matrix scaling, and you get that, okay, if you always far from mean doubly stochastic, your log norm decreases additively by this epsilon n over 6. And you get exactly that also epsilon n over 6. But then you know that you're lower bounded by this invariant. Yeah?
I mean,
Sorry.
an ancient candidate for the white eyes would be xi star, right?
Yes, but it's not always that case, right? So we have to be, you cannot guarantee an explicit one.
Do you know when they are non-zero? Characterized might depend on m, I guess, right?
No, yeah, I don't know. It's just, yeah, because it's really about this like invariant theoretic question. So it's a little more complicated than that.
So in the case that the x's correspond to the classical problem, do you, what are the ones that give you the previous invariants? And how do you see that they're not?
Right. So like for this to degenerate to the classical case, like the Krauss operators have to be all of them, all the answers, like all the EIJs for which you have support. And once you have all the EIJs for which you have support, you can match them to be the permutation. Yeah. Okay, very good. So then, so it's identical. And then we do this analysis, we're happy, right? So we also have,
Sorry, one question. So if I start from a quantum channel, so I have the property that sum xi dagger is equal to identity. Can you give me a polynomial for which this is positive, or?
No, that's the thing, right? So because if you have a quantum channel, you're only enforcing that there you have the trace preserving property. So you know that one marginal is correct. What about the other marginal?
No, I know, but like if I start from having this assumption that one marginal is correct, can you then find?
No, because you need to be able to say because.
If it's simpler to find the.
If it's simple, no, yeah, exactly. But I'm saying it's not that it's even simpler. Is that such an invariant may not exist because you need a quantum channel that can be scaled to be doubly stochastic. If your quantum channel cannot be scaled to be doubly stochastic, no such invariant exists.
But is there then a simpler criteria?
They're all zero. Sorry, no non-zero invariant exists. Yeah.
Is there then a simpler criteria?
No. Yeah.
Is this when you use the Hilbert metric, the convergence requires that it's positivity improving the map, which is very difficult to check.
Right.
Here, can you check?
Right.
Is this testable?
Yes. So it's testable by just running the algorithm, right? You can just run out the algorithm and you figure out if you converge or not.
But that's also...
Right. Oh, yeah, and I forgot to say, right? So Tryphon has a work with Michele from like 2016,
yes.
Right? That they do exactly the same analysis that Sinkhorn does for this operator scaling, but the condition that he's saying is positivity improving just means that your quantum channel just maps like every PSD to a positive definite matrix, which is equivalent, is exactly the generalization of having a matrix that has full support. Okay? And this is exactly removing that assumption from that work.
In that condition is very difficult to check in practice.
Correct. And this is also related to like this Braskamp-Lieb inequalities. Like how do you check? Yeah. So the way that we do check is by running this algorithm. So we don't look at the inequalities. Like we know how to describe them, and I can talk to you about them offline. We know how to describe these inequalities, but there are too many.
I see.
So exactly, there are too many. They form a polytope, and that polytope
in the other way, that's how also we do it. We just run it and see where it converges, but again, we don't know it satisfies this condition.
Okay, so.
Sorry, just one question. Why is it difficult to check it? You have this Wieland inequality which tells you how far you need to wait until you... no, sorry.
Okay, so let me just kind of say, okay, how does this relate in my minute left, right? How does this finally relate to like entropic optimal transport? So, so if we wanted to generalize this classical connection that we talked about in the beginning between matrix scaling and optimal transport to the quantum setting, right? What's the right divergence to use here, right? So, so you try like the usual one, the von Neumann divergence doesn't seem to work, okay? But then, it turns out that the projective KL divergence like turns out to be the right like divergence to actually use, right? So what is the projective KL divergence? So if I have like two PSD matrices, right, my KL projection is going to be the supremum over all projective measurements of the usual KL divergence. So what does it mean? This is essentially the worst relative entropy that you can get after performing a measurement, which makes sense, right? Because if you're like two like states and you're trying to say, okay, there's a divergence, well, if they're going to be close if one state can be masked as the other one, no matter which measurement you take. So it makes sense to take like the worst possible measurement, right? Okay, so Bert et al. Like in 2017 have these like variational expressions for the KL proj, okay? And we managed to use that to prove the following theorem. This is joint work with Paul Ayers, Fonch, Augusto, and Akshay, that we say, okay, if I take the Choi representation of a completely positive map, then we have that the log capacity, like minus log capacity, is going to be the infimum of the KL proj over all transport planes, okay, of X and the orbit closure of my Krauss operator. So here I do need like this infimum over PQ just tells me that I'm taking an infimum between X, like transport planes, and an orbit closure, right? And then we have the scaling factors again, okay? So, and again, this result also holds for arbitrary marginals, but I'm just stating things here for simplicity, okay? So in the 0 minutes I have, like what are the proof ideas, right? So again, the proof ideas is to follow like Oliver's mantra, right? And say, okay, let's look at the right geometry. The right geometry here is like the geometry at the level of Hadamard manifolds. And then we use this variational characterization of KL proj, okay? And once we do this, like the tools we use is some financial duality theorem, the existence of kind of exact scalings and approximation techniques. Okay, so that's it for me.
Thank you very much.